In this video, we're going to take a look at the exponential function and also what its inverse looks like. We'll dedicate the first few pages to drawing the exponential function, and later on we'll get into what the inverse is. So first of all, we're going to graph actually three different exponential functions: y equals 2 to the x, y equals 3 to the x, and y equals 4 to the x. And we're just going to use a table of values. We're going to take a few negatives from negative 3 to -1, 0, and then 1, 2, and 3 for x as well. Now, first of all, we're going to substitute -3 in place of x. So we would evaluate 2 to the power of -3. And remember, what that looks like is this. So 2 raised to the power of -3. Remember, the negative exponent means the reciprocal. So that's 1 over 2 cubed, which would be 1 over 8. So that first y value is 1 over 8. When you evaluate the next one, which would be 2 raised to the power of -2, then that would be 1 over 2 to the positive 2, or a quarter. And so the next one's a quarter. Two to the power of -1 would be 1 over 2 to the first, or 1/2. 2 to the power of 0 is 1. Anything to the power of 0 is 1, except you can't evaluate 0 to the power of 0. 2 to the power of 1 is 2, 2 squared is 4, and 2 raised to the power of 3 would be 8. Now these are all ordered pairs, so -3 1/8 means we go left 3 and up an 8, so that's pretty low, pretty close to the x-axis. -2 a quarter would be about right here, and then -1/2 here. Then 0, 1 would be this point right here. 1, 2, 2, 4, and then 3, 8 would be up here. And so we draw a smooth curve between those, and that's what y equals 2 to the x looks like. For the next one, y equals 3 to the x, so we would first evaluate 3 raised to the power of -3, so that's 1 over 3 cubed, or 1 over 27. And then 3 to the -2 would be 1 over 3 squared, or 1 over 9. 3 to the -1 is a third, 3 to the 0 is 1, 3 raised to the power of 1 is 3, 3 raised to the power of 2, or 3 squared, is 9, and 3 to the power of 3 is 27. And so we can plot those points, and we'll plot them all on the curve here. Now we can't actually plot 327 because 27 is off the top of the graph. So basically draw a smooth curve between them, and that's what y equals 3 to the x looks like. Now very similar, 4 to the power of -3 would look like this. So it would be 1 over 4 cubed, and 4 cubed is 64, so that's 1 over 64. So that first y value would be 1 over 64. And then we would have 1 over 16. 4 to the -1 is a quarter, 1 over 4. 4 to the power of 0 is 1, 4 to the power of 1 is 4, 4 squared is 16, and 4 cubed would be 64. And of course the last couple are too high to graph, but we can graph the first several. Now 1/64 is pretty difficult to graph, but we go left 3 and up 1/64, so we'll make it look like it's just barely above the x-axis. So applying the other points, and of course 0, 1 again would be here, just the same as the first two. 1, 4 would be right there. And then 2, 16, well 16 is just off the top of the graph. 11, 12, 13, 14, 15, 16 would be up there. And so we draw a smooth curve between them. And we'll label all the curves. And so that's what it looks like for the basic shape of an exponential curve. Now a couple things I want to point out here. Let's take a look at the 4 to the x. If we go from 1/64 to 1 over 16, to go from 1/64 to 1 over 16, you actually multiply that by 4, you get 1/16. If you multiply 1/16 by 4, you get a quarter. And just to demonstrate that, if we have 1 over 16 times 4. Now the 4 is the same as 4 over 1, so multiplying the numerators, 1 times 4 is 4. And 16 times 1 on the bottom, in the denominator, is 16. Now 4/16 reduces to a quarter. So that's why I say if you take a 16th and multiply it by 4, you get a quarter. So that's what this says. You take a 16th, multiply by 4, and you get a quarter. And that's the same all the way along here. Quarter times 4 would be 1. 1 times 4 is 4. 4 times 4 would be 16. 16 times 4 gives you 64. So notice for an exponential curve, as long as the x coordinates are in order and going consecutively, -3, -2, -1, etc., then the difference between the y values are all in the same ratio. There's a common ratio or product between the successive function values. And so that's what that statement says. Now, one last thing before we go on to the next page. If you have, for any of these curves, you want to find the rate of change between 2 points. So for example, let's say between this point and this point, remember you would just draw a secant, and to go from this point to this point, the average rate of change, you would use the change in y over change in x, or rise over run. From this point to this point, it's gone up 4 blocks, and to the right 1. So the rise is 4, the run is 1, or change in y is 4, change in x is 1, so 4 over 1, of course, would be 4. So the average rate of change, for example, from this point to this point on the 2 to the x function would be 4. So that's how you calculate an average rate of change. It's really just a slope calculation. Flipping over to the second page, we're going to graph and these are the 3 graphs in the first page. We're going to graph y equals a half to the x, 1/3 to the x, and a quarter to the x. And so the difference between the first page and this one is all the bases are rational numbers between 0 and 1, or fractions between 0 and 1. And so for the first one here, when we evaluate a half raised to the power of -3, that's what this says. Now, remember, the negative exponent means the reciprocal. So this is actually equivalent to the reciprocal of a half, which is 2 over 1, raised to the power of +3. So this is really just 2 cubed, which would equal 8. So that first y value would be 8. If we raise a half to the power of -2, that would be the same as 2 squared, or 4. To the power of -1, we would get 2. And then a half raised to the power of 0 would be 1, same as all the ones in the last page. A half raised to the power of 1, of course, would be half. A half squared means a half times a half, or a quarter. And the last one is an eighth. And so if we plot all these points, -3, 8, so left 3 and up to 8. -2, 4 would be right here. -1, 2 would be right there. 0, 1. 1 1/2 would be here. 2 1/4 would be down here. And then there's 3 1/8. And so if we draw a smooth curve between those, that's what the y equals a half to the power of x curve looks like. And very similar, you can graph the rest of these. And I'm just going to go kind of quickly through these. You can investigate the y values if you want. And so if we plot all the points, draw a smooth curve, that's what y equals a third to the power of x looks like. And then the a quarter, these are the y values. And so if we plot them, that's what y equals a quarter of the x looks like. Now we're going to compare these in the next page a fair bit, so I'm not going to spend too much time here. But notice that the half the power of x and 2 to the x, they're actually reflections of each other in the y-axis. Same as y equals 3 to the x and y equals 1/3 to the x. Those two orange graphs are reflections of each other in the y-axis. And the same for the 4 to the x and a quarter to the x. So comparing the graphs, now one thing I'd like you to note is that all these functions have a horizontal asymptote. In this case, it's y equals 0. If you start getting into any transformations, like for a vertical shift, for example, then it wouldn't necessarily be y equals 0. It might be y equals some other constant. But they all exponential functions have a horizontal asymptote somewhere. Now, these functions here that have a base between 0 and 1, they're completely decreasing functions. And remember, to figure out if something is increasing or decreasing, you look at the graph as you go from the left side to the right side. So these are all going down from left to right, so they're decreasing functions. The first three that we graphed, you go from left to right, the bases between is bigger than 1. Like the 2, 3, and 4. So those are all increasing functions. As you go from left to right, they're going up. So they're increasing if the base is bigger than 1. Now notice that they all go through the y-axis at the same point. So they all have a y-intercept of 1, since a to the power 0, whatever the base a is, whether it's 3 or 2 or 4 or a half or a quarter, whatever it is, raised to the power 0 always equals 1. The only exception here is you can't evaluate 0 to the power 0. That's why this restriction is listed here. Otherwise, they certainly all have a y-intercept of 1. Now, as I mentioned in the last page, y equals a to the x and y equals 1 over a to the x are reflections of each other in the y-axis. All of these functions have a domain of the entire set of real numbers. They go forever to the left and forever to the right. And I just kind of said that backwards, forever to the left, forever to the right. Now, they all have a range that is, in this case, the y values are completely above 0. They never actually touch the x-axis because there's no power of 3 or 2 or 4 or a half or whatever, that positive power that, or actually even a negative power, that will give you a value of 0 or below 0. And so the range is all real numbers such that y is greater than 0. It cannot equal 0 either. No power of a positive, whether it's a whole number like 2 or a fraction like a half, no power could ever make that work out to be 0 or negative. On to the last page, which is where we're going to talk about the inverse of an exponential curve. And so this is actually the graph of y equals 2 to the x, the very first one we graphed on the first page. And here's several of the ordered pairs from that table of values. Now, to graph an inverse, one thing you can do is just switch the ordered pairs. So for example, the point 3, 8 would become 8, 3 on the inverse. You just switch x and y. 2, 4 would become 4, 2. 1, comma 2 become 2, comma 1. And so if we take these ordered pairs, 0, 1 would be 1, 0 right here. And this point, negative a half, 1, negative 1, comma a half would be 1 half, negative 1. So over 1 half, down 1, so that point right there. And then we could plot this other one as well. And so we draw a smooth curve between them. And so that's what the inverse of y equals 2 to the x looks like. Now, we switched for all the ordered pairs x and y, so in the equation you do the same thing. So y becomes x and x becomes y. So the inverse equation would be x equals 2 to the power of y. So the inverse of y equals 2 to the x is x equals 2 to the y, and that's what the graph looks like. Now, if the base is greater than 1, as in y equals 2 to the x, notice that the exponential curve y equals 2 to the x and its inverse are both increasing functions. So they increase as you go from left to right, and this one does as well. It never ever goes actually horizontal. It does keep increasing. Now, if the base is instead between 0 and 1, like the half to the x and the third to the x in the previous pages, then that's an example of that kind of graph here, the red one here. Y equals b to the x, where the base is between 0 and 1, looks like this, so it's a decreasing function. And if we were to graph its inverse, this is what the inverse would look like. This is the x equals b to the power of y. It's also a decreasing function. So if the base is between 0 and 1, they're both the exponential curve and its inverse are decreasing. If the base is greater than 1, then they're both increasing functions. But that's what the inverse looks like. This dotted line here is the line y equals x, and the reason it's there is because the inverses are actually reflections across that line. And that's why 3, 8, for example, becomes the point 8, 3 in the inverse. They flip exactly across the line y equals x. So it's kind of like this point's flipped over to here, this point's reflected over to here, this point's reflected over here, etc. They're actually vertically opposite of that dotted line, of course the same distance from the dotted line, one on one side, one on the other. So that's what the inverse of an exponential curve looks like. And that's the end of the lesson.